we start off with the skeleton molecule here. Sulfur with 3 oxygens, right? And then we count up electrons. Each sulfur brings 6, or the sulfur brings 6. Each oxygen brings 6. That's a total of 24 electrons that each atom brought to this party, right? And we put a +2 because why? 2 extra electrons. That's what that -2 charge is indicating. Okay, so 26 valence electrons. I see that 2, 4, 6 are already up here. So I need 20 more. All right, I'm going to start putting electrons here because sulfur doesn't have 8 available to it. Now it does, right? Now it has 8 available to it, right? Before it had 6 available to it. Now it has 8 available to it. 1, 2. And then I'm going to go 1, 2, 3, 4, 5, 6. And I see that I have 18. So I'm going to do that on all these oxygen atoms. Okay? So that uses up all our electrons. Now we use formal charges to help us identify the correct compound, or correct electron density, how the electron density is arranged around this polyatomic ion. Okay, formal charges. What are the formal charges on these oxygens? They're all in the same condition, right? What's their formal charge? -1. Oxygen brought 6 minus the number of electrons right around it. 1, 2, 3, 4, 5, 6, 7. So that's how you do that. Okay? Each electron that's in lone pairs counts individually, and each bond just counts as a single electron. So that's a -1 formal charge on these oxygens. And what's the formal charge on the sulfur there? What? +1. +1, right? It brought 6. It has how many? 5 right around it. Okay, can everybody see that? All right, so this does not look like the best compound. Why doesn't it look like the best Lewis dot structure for this molecule? Because we have a negative formal charge and a positive formal charge right next to each other, right? Everybody has a formal charge. Okay, some strong indicators. The formal charge is the strongest indicator to whether or not you have a good compound. Now we do expect a net formal charge of -2 on the compound, so we're not going to be able to get rid of that. But if I bring electron density from one of these oxygens in, right, and then I end up with something like this. Oops, there's 2 more electrons on there, right? Now, all I did was bring these electrons and make them into a bond. Now this doesn't have a formal charge, the sulfur doesn't, and these 2 oxygens have a -1 charge. All right? I might think, okay, let's see what happens if I bring my electrons in here. Some electrons from one of these oxygens into a bond. That would result in like that. Now these oxygens both have no formal charge on them. And this oxygen here has a -1 formal charge. Right? What's the formal charge on the sulfur? -1. Is that right? It brought how many? 6, and it has 1, 2, 3, 4, 5, 6, 7. So now we have the formal charge on the sulfur. So which one of these 2 compounds is most correct? And why? That one, why?
Because the electronegativity is on the oxygen.
Why on the oxygen here?
Because it's more something.
Electra rhymes with tegative. Very good. It's more electronegative. So we want the charge to end up on the more electronegative atoms. Okay? So this is what our sulfite ion looks like. Okay? And if I have this sort of a scenario where I take a proton and add it to the SO3 2 minus ion, what I'm doing is I'm taking the sulfur, oxygen, 2 negative charges there, and the hydrogen ion is coming on right there, resulting in the HSO3 minus ion, the bisulfite ion. So the hydrogen is connecting to an oxygen, right? And that's how oxyacids work. Oxyacids take the proton by way of the oxygen because that's where the electron density resides. Okay? So, let's see, we got to erase this really quick and give ourselves a little bit of space because at this point here, actually I just erased what I wanted to have up here. But before we got to this point, remember the electron density was over here like that, right? And we pulled it in to form a double bond. I could have pulled the electrons from here or from here, right? And symmetrically, it would be the same compound. I mean, if you spun it around, it wouldn't look any different, wouldn't be any different. But there is a difference because those are different oxygen atoms. And if I were to instead bring the electron density down from below, whoops. Okay? I have what are called resonance structures. The electron density is moving, capable of moving from the oxygen out here, these electrons, these lone pair electrons, and come in and form bonds. So this might come in, and then when it comes in, well, let's actually draw this arrow on this side over here. These electrons came in, and when they came in, these ones had to get pushed out. And then the result was this structure over here. Can you see that? And those are called resonance structures. We could have a third resonance structure, right? Where, what would be the difference in our third resonance structure? What would this molecule do to make the third resonance structure? Yeah, the electrons would come in from here, and what would happen over here? This double bond would pull out and make lone pair electrons there. Okay? So, small little one up here. With that being another possible resonance structure. So this can shift, and does, very rapidly between these different, what we call resonance structures. The electrons are kind of moving around, resonating in different regions. Now, there's a difference in the length of bonds. For example, a carbon-carbon bond is longer than a carbon-carbon double bond. And a carbon-carbon triple bond is shorter yet. Okay? Same with a sulfur-oxygen bond. Sulfur-oxygen double bond is shorter than a sulfur-oxygen bond. And that should be a little bit intuitive to us because here we have more electron density being shared. So the increase in sharing allows those atoms to come closer together. Okay? If we said that the length of this sulfur-oxygen bond here is 100 picometers and the length of this one is 120 picometers, okay? So I'm just providing you a little key here showing you the length of these bonds. And we thought about this molecule. If this molecule is in water just tumbling around, because it has the ability to kind of change between its resonance structures, the resulting length of these bonds wouldn't be distinguishable. They would all look the same because they would basically all be changing all the time. So you would have to determine the length of this sulfur-oxygen bond based on the average. Okay, so this length is how long, this sulfur-oxygen bond? 120, this one? 120, and this one? 100. So what's the average length of those bonds? How would you do that? Add them up and divide by 3. Does that make sense? So because it's in a solution like that, and these resonance structures would be changing between each other, then the actual length of this bond would look like the average of those bonds. Okay, let's see. I think that we're pretty much ready to move on to chapter 10. And chapter 10 contains